All right, but that's what we got. Cool. So welcome to week 2. Um, any questions before we continue talking about sets and set theory?
I have a question on the homework.
Okay.
For a couple of the questions, it references like where n is in the set of double strike p. Is that supposed to be the power function?
Double strike P is probably a set of positives.
Okay, I was looking online and I couldn't figure out what it was.
Do you have a particular question that we can look at?
Yeah. Hold on.
Okay.
Is there somewhere in the book that tells us what all these weird double strikes?
Yeah, that's what I was going to look for if I could see the actual symbol.
Okay, cool.
So there's a few of them out here on page 13. Naturals, integers, rationals, reals, and complexes.
Oh, sorry, I don't mind my screen. There's 2 questions, particular section 1.1, questions 2C and 2E.
Okay, is it this symbol here?
Yeah.
Okay, yeah, so that seems to be the positive integers. N is the naturals, which are positives, plus 0. Z is all integers. Q is rational. R is real. C is complex.
Okay. Yeah, I missed that because it wasn't in the list, and it was confusing me because there wasn't like any specific consensus online. It can represent either prime numbers, a power set, irrational numbers, or forcing a posit, whatever that is.
And that's a good thing to ask about because there is Z and Q are pretty standardized. N is not standardized. Sometimes it excludes 0. R and C are pretty standard, but yeah, it's always good to double check those.
How would you pronounce each of those symbols? Like, what is there a different name that they're called other than the wacky symbol?
I just call them by the letters or by the thing they stand for. But in class, I talk about the funny Z with 2 lines on it.
They're called double strike or blackboard bold.
Okay. Cool. Yeah, I figured there was
standard. Sometimes you look up double strike letters, and it's a different kind of double strike. Like you might see a double strike in a Y, which means yen.
Okay,
Kind of
right.
Strike.
Yeah, I figured there was a better name though than funny Z with 2 slashes. All right, other questions on homework or otherwise?
Okay, just confirming. Yeah, it is usually called blackboard bold.
Okay. Cool.
What was it? It's called black or bold?
Yeah, blackboard bold.
Oh, blackboard bold. Okay.
Sounds like a type of car. Let's see, 222 question. If my partner drops 222, what should I do with the SLP? You probably have to continue on your own. And you may adjust the goals and milestones and such accordingly. But yeah, this happens sometimes in group projects, sometimes in job situations. Somebody you're working with stops being able to work on it, and what do? So you have to make adjustments.
I have a question.
Mm-hmm.
On number 8 of 1.2, I tried A, B, and C, and then I got stuck on D and everything afterwards. And that was just try this, make a try at this. But I'm kind of curious about it.
Ah, okay. So you managed to do, you said A, B, and C?
A, B, C, and then got stuck on D, and then didn't do anything after that because I got stuck. I was like, well, I could do it this way, but then I started overcomplicating it and overthinking it, and I was like, I don't think it's supposed to be this way. So
it can get pretty complicated. But let's see, we have all students, so we know the universe, day students, math majors, grad students, and so day graduate non-math majors. So if you could find all the graduate non-math majors, so day graduate non-math majors, so they need to be in the set D, which is daytime students. They need to be in the set G, which are graduate students. And they need to be non-math majors, so they need to be in the complement of M. So you're looking for the number of students in that set. And I'm just kicking around some ideas here. The complement of this would be students who are not day students or not grad students or math majors. And if you can find the number of elements in here, you can find the number of elements in here because it's just the whole universe minus that many. And we have this simple version of addition subtraction which says the number of things in A union B is the number of things in A plus the number of things in B minus the number of things in the overlap. But this rule actually gets a lot more complex with three things. If you have the intersection, the union of A, B, and C, and you want to find the number of things in there, it's the sum of the cardinalities minus some other stuff plus some extra stuff because you end up subtracting too much. And so that can make things tricky, but you could also try going about it like think of it as the union of this with that. And so break it into a sub-problem, try to find the number of things in this set. But yeah, keep messing with it and don't worry if it becomes overly complicated. As I said, I'm not going to grade this one for points. So, you know, don't fail your physics homework because you spend 3 days working on this. But give it some thought and play around with it and get a feel for how these things interact with one another. And when we get to counting, we'll go through the formal rule for finding cardinality of the intersection of three sets. And if you have that rule, and this is pretty straightforward. Anybody else get any further on these? All right. Well, that got me through my lunch at least. All right. Well, let's look at computer representation of sets. So we know what a set is, right? It's a collection of objects, and we have this notion of if we pick any object in the universe, we can ask, is it a member of the set or is it not a member of the set? And so even though these things are unordered, what we can do is we can pick an artificial ordering. So we're going to order the elements of the universe. So suppose our universe consists of A, B, C, D, E. So we have 5 elements in our universe. And we want to describe a set comprised of things from this universe. So what we can do is we can assign an ordering to these elements. And let me just, do first, second, fifth. And for any set, I'm going to write a 5-bit number. So for example, let S be the set containing A, D, and E. Alright, I'm going to represent this as a 5-bit number. And what I'm going to do is I'm going to write a 1 in the first bit position if E is an element of my set, and a 0 if it's not. So since E is contained in my set, I'm going to put a 1 right here. Since D is contained in my set, I'll put a 1 here. Since C and B are not in my set, I'll put zeros there. And since A is in my set, I'll put a 1 there. And so this will be the 5-bit number corresponding to my set, ADE. Now my sets are still unordered. If I picked a set like, D, E, A, I'm going to get the same 5-bit number, right? A is in my set, B and C are not in my sets, D is in my set, E is in my set. So we haven't made the sets ordered, right? But to do this mapping from sets to binary numbers, we're creating an artificial order on the elements in the universe. And so, I could let T be the set B, C, D. And so that would correspond to the number 0, 1, 1, 1, 0. Everybody get the idea of how I'm doing this mapping to binary numbers?
Yes.
So if I have this mapping, I can do the following. For example, suppose I want to take the union of two sets, S union T. Well, I know S union T would be everything in S and everything in T. Well, that's A, B, C, D, E. That's like the whole universe. Well, if I write that as this binary number, it's just 1, 1, 1, 1, 1. But guess what? If I take this, and I take this, and I logically OR them bit by bit, 1 or 0 is 1, 1 or 1 is 1, 0 or 1 is 1, 0, 1, 1, 0. This number is just the bitwise logical OR of this number with this number. If I take the intersection, so what are the things in S and T? Well, it looks like it's just A, B, C. It looks like it's just D, which would look like that. Well, this is the logical bitwise AND of this number and this number. So 1 and 0 is 0, 1 and 0, 0, 1, 0, 1. Those are all zeros. 1 and 1 is 1. That's the logical AND. And if I wanted to take a complement, so if T is B, C, D, then the complement of T would be A, comma, E, which would be 1, 0, 0, 0, 1. Well, this is just the bitwise complement of that. Take each 0, change it to a 1, take each 1, change it to a 0. So once we make this representation of sets as binary numbers, we can do Boolean operations on these numbers, and those correspond to set operations on the original sets. And so this is a really convenient way to represent at least finite sets in a computer, as long as the universe isn't too big. if we wanted to represent all numbers between 0 and 1,000,000, we'd need, 1,000,001 bits to do this, so that doesn't work very well. But for small universes, this is a useful way to represent things, and it's a useful way to think about set operations. One more little ditty. If I've got 5 bits, how many different ways can I write a string of 1s and 0s containing 5 bits?
2 to the 5th.
2 to the 5th. Well, if I think of this as just a set, it's the universe, but I just think of it as a set, right? Every set I write is basically a subset of this. Every subset corresponds to a 5-bit number. Every 5-bit number corresponds to a subset. Since there are 2 to the 5th possible numbers, that tells me I have 2 to the 5th possible subsets. The set of all possible subsets is the power set of the universe. The number of things in that, we've seen before, is just 2 raised to the number of things in the universe. So this is another demonstration of the fact that if you have a set containing n elements, you have 2 to the n possible subsets, corresponding to the 2 to the n possible n-bit patterns that you can write. Alright, let's talk about functions. So we deal with functions in math courses. We know that logarithm is a function, square root is a function, cosine is a function. But let's think more abstractly about what a function is. Functions in programming languages are things that you feed numbers to, typically, and you get a number back. Could be characters or strings or whatever, but we can certainly define functions that you call by passing numbers to them, and they return a number back. And that's a more general version of, like a square root function or a cosine function. So let me give you a more formal, more general definition of a function. So a function f colon a arrow b is an assignment or a mapping of a single element little b, which comes from the set B, for any element A in A. And we call this element little b, we call that f of little a. So pictures, we've got some points over here in B. Let's say we've got 3 points over here in A. Here's a function. Ta-da, function. It's an assignment from each point of A to exactly 1 point in B. Right, and we're just thinking of these as sets. There's no math going on here. It's a set. It's a set. Every point here gets mapped to exactly 1 point here. That's a function. And there may be points here that aren't mapped to. That's okay. And there could be multiple points in A that map to the same thing in B. That's okay too. To be a function, all we need is that every point in here maps to exactly 1 point over here.
Is this touching on finite state machines?
No.
Okay.
We will touch on those though towards the end of the course.
Okay.
I'm
Or yes,
confused.
more states, but yeah.
Okay.
What is, so this A maps all of its elements into B, or?
F maps elements of A into B.
Okay. Every one of them just goes into B?
Mm-hmm. Yep.
So it's like taking A and putting it into B, that's it?
That's it. Yeah.
Basically, we're just adding it, correct?
We're just what?
We're basically adding it, or is this just a placement?
This is just an assignment. For each element in A, we're assigning an element in B, so we're just pairing these things off. Everything here gets associated with something in B. So let's do some examples. Examples are better. Suppose A is the set 1, 2, 3, and B is the set Q, R, S, T, U, V, W. So here's our set A, here's 1, 2, 3. Here's our set B, and here's Q, R, S, T, U, V, and W. I really need a pencil now. Alright, so here's an example of a function. Here's an example of a pencil that kind of works. I'm going to map 2 to S, I'm going to map 3 to R, I'm going to map 1 to Q. Alright, that's a function. And I could represent this by saying, you know, what does F take each of these things to? So, you know, F is what I'm calling my function. And I could describe this function by saying f of 1 equals Q, f of 2 equals S, and f of 3 equals R.
Okay, that makes sense. And so it just goes in order from A1 connects to B1?
Basically, yeah. In this case, this element is associated with Q, this element is associated with S, this element is associated with R. So it's a map. It's saying, you know, give me a letter, give me something from A, I'll give you something from B.
So similar to the binary position.
Yeah, similar. So here's a totally different function. Right? This function takes 1 and maps it to U, it takes 2 and maps it to S, it takes 3 and maps it to R. So any kind of association between the elements of A and the elements of B, that's a function. Now here's something that's not a function. Suppose I said that 2 is associated with both S and W. It's not a function. Right? I have to have one thing exactly over here associated with each element in A. This is the vertical line test that you learn in math classes.
Question.
Yeah.
In the before, you stated that 2 pieces of A could be placed into B. Does that mean that it could equal, like, 2 and 3 could be equal to S?
Yeah, so I could have a function that looks like this. And f of 2 would be R, and f of 3 would be R. That's still a function.
So it's one way, not the other.
It's one way is fine, the other way is not. We've also, you know, in this case, we've got things over here that nothing is mapping to. That's totally okay. So let's make a different example of a function. A and B are going to be the sets of integers. And I'm going to define a function f which maps elements of A into elements of B. And I'm showing you some of the elements of A. There's you know, all the integers are in there. But let me show you what some of these functions, some of these points map to. So the element 1 maps to 1, the element 2 maps to 4, the element 3 maps to 9, negative 2 maps to 4, negative 1 maps to 1, negative 3 maps to 9. Well, this is a function we're familiar with. This is the function f of x equals x squared. Presumably. I've only shown you 7 points, but that's the function I had in mind. So we can write this function of f of x equals x with a superscript of 2, and we know that means multiply by itself, and we can define multiplication and all of that business. But we can also define this function simply by stating what each element here maps to over there. And we forget about math, forget about exponents and algebra and all that stuff. We can define this function just by listing what each element in here maps to over there. I could define, you know, a function that doubles a number. I could map 1 to 2, 2 to 4, 3 to 6, negative 5 to negative 10. That's a different association from integers to integers that corresponds to the function f of x equals 2 times x. I could go from reals to reals, and I could define the sine function that takes, you know, any number and maps it to some number between positive 1 and negative 1. And for every number, every real number over here, all I have to do is tell you what the number is that it maps to. That's the sine function. And if you think about this a little further, it means we could replace every mathematical function we ever deal with just a big table. Just something that lists, you know, the value of the function at all the different points that you might calculate it at. And so people used to do this before calculators were a thing. You would have a book of function values, and there'd be a chapter on logarithms and a chapter on sine and cosine and a chapter on tangent. And if you wanted to know what the sine of 45 degrees was, you would go to the chapter on sines and cosines, and you'd flip to the page that listed, you know, 45 to 45.5, and you'd find 45 and read across the page, and there would be the sine 0.707, etc. Is this making sense? I can't tell if it's totally confusing, totally obvious, or just bizarre, or...
It makes perfect sense.
Bizarre to me.
Okay.
At least this part of it. I got the one before this kind of went sideways.
Okay.
Maybe you should demonstrate with a Cartesian plane.
Well, so let's think about a graph. All right, so if you draw a graph for a sine wave, I know I'm doing some flashbacks on people here.
Some horrible flashbacks.
Yeah. But we're just going to think of this as a thing that says, you know, for a particular value here, x, what's the corresponding value of y? Well, we can read it off the graph, right? We're not going to do unit circles or weird things like that. If I want to know what the sine of 30 degrees is, you know, or pi over 6, I can go to that point, and I can come up here and see where that graph is, and it's at 0.5. Well, bingo, I'll decree the sine of 30 degrees is 0.5. Why? Because that's where this curve tells me it is. But, you know, I could also make a table. I could call it x and sine of x. And 0 would be 0, and 0.1 would be something, 0.2, 0.3, 0.9, 1.0, and so on. And I could just list, you know, what the sine of each of these different points is. And if I wanted to know the sine of 0.2, it's, you know, whatever I wrote right there. If I want more accuracy, you know, I would have more rows in my table. I'd start off with 0, and I'd do 0.01, 0.02, and so on. And if you imagine, you know, a really, really detailed table with like every possible real number here and the value of the sine of that real number written next to it, that's, you know, that's the sine function. That's what it is. It takes a number and it gives you another number. And so we can think of sines as just going from some set of real numbers into some other set of real numbers, and each point maps to something over here.
That helped.
Okay, cool. All right, good suggestion. Whoever said Cartesian then.
Yeah, and then it follows, if you remember the vertical line test, if there were two values for any x point on that plot, then there would be two values for the output of the function, and then that doesn't make sense.
Right, right. So if some point over here is actually mapping to two different spots, it means that point corresponds to, you know, this value, but maybe also some other value up there. And so if you do the vertical line, you'd see that it hits the graph in two spots. It's not a function. So we can think of functions mathematically, right? We know we can write like a Taylor series for the sine of x and add up, you know, this big, long, horrible expression and so on. Or we can think of it as, you know, angles and hypotenuse and all that stuff. Or we can think of it as, you know, an association of values with function values. Or we can think of it as just this assignment. So, function f going from a to b, where we can write something like this. We can say the number a gets mapped to some number that we're just going to call f of a. Right, and f of a is the thing in b that a is mapped to by this function f. Well, here's a totally different way to describe a function. We can simply list tuples, remember a tuple is an ordered pair, so we can list tuples where the first thing is a number from A or an element from A, and the second thing is the thing in B that this is mapped to. So for example, f of x equals x squared, and let's say it goes from integers to integers. Well, we could describe this function by listing a bunch of tuples. For example, 0 will go to 0, 1 will go to 1, 2 will go to 4, 3 will go to 9, negative 1 will go to 1, negative 2 to 4, negative 3 to 9, and so on. Well, how do I describe a collection of something? Let's make it a set. So I could take the set containing all of these tuples, and that set is in some sense exactly the same thing as this function. Well, more generally, if I have just some function f going from A to B, I can describe that function as a set of tuples where these first things come from A and the second things come from B. Well, do you remember something we talked about that had to do with tuples where the first element comes from one set and the second comes from another set? You got a homework question on it involving dice and coins. Remember
I'm not gonna lie, I spaced out for a second. What was the question?
something that we've talked about that you have a homework question on that involves tuples where the first element comes from one set and the second element comes from a different set. There was a concept we discussed.
Do you remember what question it is? I remember remotely that there was a coin question, but I can't remember which one it was. Looking at my homework now.
Okay. It was about rolling a dice and flipping a coin.
Oh, that was the 2 to 6 one, was it?
Yeah.
And you had to treat them like you had 2 available of the coin and 6 available of the dice possibilities.
Right.
And you had to figure out how many possibilities would factor in if you did both of them together. Where was that?
Like permutations or something? I don't know.
Similar to that. 2 words.
Cross product?
Yeah, cross product or Cartesian product. Awesome. So we had this notion of a cross product. A cross B, or the Cartesian product of A and B, is the set of all tuples little a, little b, where little a comes from set A and little b comes from set B. Well, we're saying that if we have a function f going from A to B, we can think of that as a set of tuples where we list the elements of A and associated with each one some value of B that we call f of that value of A. In other words, this function corresponds to a set of tuples where the first element comes from A and the second element comes from B. Well, that's just a subset of A cross B. So every function corresponds to some subset of this. Well, if we were to write all possible subsets of A cross B, that's just the power set of A cross B. This contains every possible function from A to B. Which means, if we take the reals cross the reals, and we write the power set of that, this set, which is huge, contains every mathematical function you've ever studied the whole time you've been in school. Addition, subtraction, multiplication, division, square roots, squares, cubes, cube roots, logarithms, sines, cosines, hyperbolic, arctangents. Every function is contained in this set. And there's a lot of things in here that aren't functions at all, that fail the vertical line test. But every function that we can think of mathematically from the reals to the reals is an element of this set. That's a big set. Alright, we're not going to have to do anything with that, but it's a sobering realization that, you know, this set of 6 symbols captures the totality of like all the math we've probably ever studied in terms of functions from numbers to numbers. Alright, so terminology. Function going from A to B. This set A is called the domain. It's the set of things that you are mapping. B is sometimes called the codomain. It's the space of things that you are mapping into. If we take a particular point A and we map it under F, this is called the image of A. So we can think of this as like, you know, a projector. You shine a projector on A and you get things in B. And so I'll do some parallel example over here. Let's do f of x equals x squared, where x goes from the integers to the integers. So the domain is the integers, the codomain is also the integers. The image of 5 would be 25. The image of negative 5 would also be 25. The range of f or sometimes the image of f is the set of all f of A, where A comes from the set A. The range is the set of points you actually map something to. This is sometimes written f of big A. So this example over here, where f goes from the integers to the integers, the domain is the integers, the codomain is the integers, but the range is not the set of all integers. The range is the set containing 0, 1, 4, 9, 16, 25, and so on. It's a subset of the set of integers. But for example, there's no integer x whose square is equal to 2. So 2 is not part of the range. It's part of the codomain, but it's not part of the range. Does that make sense?
You're getting linear algebra flashbacks.
Cool. Definitely related. Alright, so So that's range domain and codomain. All right, equality of functions. Suppose we have f going from a to b, and we also have another function g going from a to b. If we say f equals g, that means f of little a equals g of little a for all points a in the set A. So it means the functions map points to the same value. So for example, I could define a function g of x, which takes negative x and squares it. Well, g of x and f of x always map points to the same value. G of 5 would be negative 5 squared, which is 25. G of 5 would be the same as f of 5. And in fact, g of anything would be the same as f of anything. So f and g would be the same function, so we could say f equals g. We can add functions. We can define a new function f plus g. And f plus g of some point a is just going to be whatever f takes a2 plus whatever g takes a2. So for example, maybe f of x is equal to x squared and g of x is equal to 2x. So f of 5 would be equal to 25, g of 5 would be equal to 10. F plus g of 5 would be equal to f of 5 plus g of 5, that would be 35. This is a new function. It's a function that takes a number and maps it to whatever f maps to, whatever g maps to, added together. So we can do arithmetic on functions. We do this in computer programs all the time. You write a function, you know, integer f parentheses something, integer g parentheses something, and you might make a function that, you know, takes a value, calls f, calls g, adds the results together, and returns that. That would be your function that we're calling f plus g. If this was a different kind of class, we could do a whole course on this notion, because we can add functions, subtract functions, multiply functions, divide functions. We can do calculus on functions. We can find the limit of a sequence of functions. We can do all kinds of crazy things. We're not going to do that. So a function is just an association of each element of A with an element of B. And so f plus g is a different association. Takes every element in A and associates a different element in B. And we usually write functions like f of x equals x squared and so on, but I mean we can also define functions. Here's a function f from the integers to the integers. F of n equals the rightmost digit of n. So f of 17 equals 7. F of negative 125 is equal to 5. F of 11 equals 1. And so on. It's a perfectly well-defined function. It's just kind of a funny way that we've written it. Take the rightmost digit of n. We could define a function that gives you the sum of all the digits in n. That's a perfectly defined function. If fact, we'll do that in a couple of weeks in 222. It's going to be called a hash function. All right, so one more thing to cover on functions. This is properties of functions. So let's stick with our picture of two clouds, A and B, and a function f that takes points in A and maps them to points in B. And we've put no restriction on this mapping other than, you know, each thing here has to map to something there. But we can impose some restrictions. And depending on these restrictions, we get different properties of these functions. So f is called surjective if everything in B is mapped to from something in A. In other words, if we have points over here in B without an arrow pointing to them, that function is not surjective. But if every point over here in B is mapped to from something in A, then we say the function is surjective. And this is sometimes called onto. And it basically says B is not bigger than it has to be. There's not extra stuff over here that's not involved in the mapping. All right, another thing. I said that it's perfectly legal if, for example, two different points map to the same point over in B. If that's not the case, though, if different points in A always map to different points in B, then f is called injective. Sometimes called one-to-one.
Someone's audio is like barely noticeable, but it's driving me nuts.
Oh. All right, everybody's muted. If you want to talk, go ahead and unmute. So injective means that different points in A always map to different points in B. So if this point maps over to here, it's no longer injective. If this point maps to here, it's no longer injective. But if this point mapped to, you know, a different point, and every point over here mapped to something different over here, then our function's injective. And injective and surjective, more or less unrelated, right? I could still have other points over here that aren't mapped to, and my function might still be injective. Or I might map to every point but my function is not injective because these two different points map to the same point. If a function is injective and surjective, it's called bijective. So it's injective and surjective. It's also called one-to-one and onto. And it's also sometimes called a one-to-one correspondence. So everything here corresponds to something there and vice versa. And I'm guessing you've heard these terms in other classes somewhere.
One-to-one correspondence sounds really familiar. Not sure from where though.
Okay.
Injective is definitely a new word.
Okay. Injective, one-to-one, yeah. So, let's take f going from the integers to the integers. And let f of x take a value x to x squared. So, is that surjective?
No, because the codomain is not equal to the domain.
Right, so it's not surjective because, for example, there's no x that maps to 2, right? 2 is a number over here, but there's nothing over here that maps to 2. In other words, 2 doesn't have a square root that's an integer. So it's not surjective. Is it injective?
Yes.
If that
No.
involves, no, it has negative numbers.
Yeah, no negative numbers.
Yeah, it's not injective because, for example, f of 1 is the same thing as f of minus 1. So it's not surjective because f of x is never equal to 2, for example, or 3 or 5. It's not injective because two different numbers, 1 and minus 1, have the same function value. Alright, how about f of x equals 2x, where again we're going from the integers to the integers. Is this going to be surjective?
No.
Why not?
Again, we'll be skipping, like, some numbers. Skipping 3.
Yeah, we'll skip 3. There's no function, there's no value x that maps to a 3. So we're missing some numbers. Is it injective?
Yes.
It's definitely injective. The only time that f will map two things to the same value is if those two things are exactly the same. F of 5 is equal to 10. And that's the only value that gets mapped to 10 is 5. Alright, how about f of x equals x plus 1, still going from integers to integers? Is that surjective?
Yes, but it's a weird thing with infinity.
Yeah, but it is surjective. Any number that we think of, we can find a value x that when you add 1, you'll get to that number. So the number 10 skrillion is mapped to by, 9 skrillion, 999, whatever, etc. Because if you take that number and you add 1, you get 10 skrillion. So yeah, it is surjective, but it does feel weird at the edges. Alright, is it injective?
Again, yeah.
Yeah. Because if I have different values of x, I'm guaranteed to get different values of x plus 1. Alright, so those are just some examples.
Break time?
Yeah, my clock just chimed. Let's go ahead and do a break. So we will come back at, let's see, 14:01. Let's come back in 5 minutes. You what? Yeah, that's cool. But it doesn't bother me if you're out here. All right, so let's continue. Let's talk about sequences. So, informally, a sequence is something like this. Right? It's my camera is gone. It's a set of things separated by commas, and they're ordered in this case. A sequence is an ordered collection of things. And it could be, you know, an infinite sequence like this. It could be, you know, a 1, a 3, a 1, a 2, and a 1. It could be a sequence containing only 5 things. Right? And because it's ordered, there could be repeats in here. Right? And it could be a sequence of, you know, things coming from any collection. So it could be a sequence of letters like an H followed by an E, followed by an L, followed by an L, followed by an O. That's a sequence of characters. So informally, we're thinking of a sequence as just, you know, an ordered collection of things, possibly finite, possibly infinite. But we can think of it more precisely as a function. So we can describe a sequence is a function f going from some subset of Z into some other set S. In this case, it's a function going from the set 1, 2, 3, 4, 5 into the set, you know, containing lowercase letters, for example. And my function, remember, it's an association. Let me write this more cleanly. A function is an association, which for each thing in this set gives you something in that set. So this sequence, HELLO, is a function which basically takes the number 1 to H, takes the number 2 to E, the number 3 to L, the number 4 to L, and the number 5 to O. So functions also let us capture sequences, which, by the way, eventually we'll use to grasp the notion of strings, right? So what's a string in C? It's a collection of characters, but they come in a particular order. Well, we can associate that with a function, which maps, you know, consecutive integers to letters in this case.
Yeah, I was gonna ask if this was along the lines of arrays.
Mm-hmm.
That was too narrow of a scope, but
Yeah, so an array is basically a sequence, exactly. An array of doubles would be a sequence of doubles. And our function in that case would go from 0 through the length of the array minus 1 and map each of those integers to a double precision floating point, which would be, you know, the number stored in the corresponding position in the array. So all of the stuff we do in computer science, you know, it wasn't just kind of dreamed up out of thin air. More often than not, it's an implementation of something that is already, you know, well defined mathematically or logically, and turns out to be really useful when we're writing programs. So we can think of a sequence as a collection of these elements, and sometimes we might write a sequence like this. Right, where we have the elements represented as A followed by some subscript. And the idea would be, you know, A subscript n is this function's value when we evaluate it at the number n. So here's some unfortunate notation. Sometimes we'll write curly bracket A subscript n to mean this sequence. And that's an unfortunate abuse of notation, because this makes it look like a set. But, you know, these an might not be distinct from one another. This is not a set. This is a different use of curly brackets. Totally different symbology. But if you have a sequence of elements and those elements are described with something like A subscript n, if you see A subscript n inside curly brackets, it might be referring to the sequence itself, this ordered collection of elements of some set. So some examples of sequences, besides, you know, those sort of artificial examples of a few numbers, A subscript n could be 1 over n, where n is a positive integer. This would be the sequence 1, 1/2, 1/3, 1/4, 1/5, and so on. It's an infinite sequence, has a number of an infinite number of terms. And this is like a discrete version of the mathematical function 1 over x. If you were to plot this, it would give you a series of points, but those points would lie on the curve for y equals 1 over x if you actually drew that curve with real numbers.
So the sum of the series would be, or the sequence, I guess, would be 2.
Actually, this sequence adds up to infinity. If you keep adding it, it gets bigger and bigger. It does it very slowly, but if it was powers of 2, a half, a fourth, an eighth, a 16th, then yeah, that would add up to close to 2. And so we encounter lots of different sequences, and we'll work with examples of these. All right, so let me give you a definition. So a recurrence relation for a sequence and here's that unfortunate notation. So this is a sequence, not a set. A recurrence relation for a sequence whose terms we call A subscript n is an expression for A subscript n in terms of other members of the sequence. me say prior. Alright, this is something we're going to come back to multiple times in this course, and this is going to tie directly into CSE215. So let me give you a bunch of examples of this. For example, here's a sequence 1, 2, 4, 8, 16, and so on. And so, for example, a of 1 is 1, a of 2 is 2, a of 3 is 4, a of 4 is 8, a of 5 is 16, and so on. And if we're kind of clever, we can find a formula for an, and it's going to be something like 2 raised to the n minus 1. But if we're a different kind of clever, we may simply make the observation that the nth term is twice the n minus first term. This is what we mean by a recurrence relation. It's an expression that describes the nth term as some function of the prior terms in the sequence. So as soon as you say something is an important point, you're kind of saying like everything else I've said has been unimportant. So I don't really want to say that. But this is a really important point. The other stuff is very important, but this is really, really important, right? So a recurrence relation for a sequence describes each term as some function or combination of prior terms in the sequence. So for example, here's a sequence of integers, and it's described by the recurrence relation that the nth term is twice the n minus first term. Okay, everybody see that? Suppose we have a sequence which looks like this. I should not have put these inside curly brackets, by the way. So suppose we have another sequence which looks like this. 1, or 0, 5, 10, 15, 20, 25, 30. A recurrence relation might be a subscript n equals a subscript n minus 1 plus 5. In other words, if I know the n minus first term, I can add 5 and find the nth term.
How does that work for the first term? Can you have a with negative n?
That's a good question. So this does not describe what a subscript, for example, if this was 1, what a1 is, because if this is a1, this formula tells me a1 would be a0 plus 5, but there is no a0. So when you use a recurrence relation like this, we usually have to specify what's called an initial condition. And so, for example, I might say something like a1 is equal to 0. And so over here in this previous example with powers of 2, I could have an initial condition like a1 is equal to 1. And if I don't specify this initial condition, and someone says, what's a6? Well, I can say what's twice a5. Okay, what's a5? Well, it's twice a4. What's a4? It's twice a3. I can get down to what's a2? It's twice a1. What's a1? Well, it's twice a0. What's a0? It's twice a minus 1. I'm never going to stop. I'm going to do that for the rest of my life. And I'm never going to figure out what a6 was. But if I have an initial condition, eventually I'll get down to what's a2? It's twice a1. Oh, a1's equal to 1. Okay, well then a2 was twice that, so that's 2. And what did I say a3 was? Oh, it's twice a2, so it's 2 times 2 is 4. and I can pop back up, and eventually I'll say, oh yeah, A6 is twice A5. That's 2 times 16. That's 32. And you're going to see this multiple times over the next 9 weeks, both in here and in CSE222. This is going to show up in mathematical induction. It's going to show up in doing proofs. It's going to show up in doing recursive algorithms in data structures. All right, what about sequence 1, 2, 3, 4, 5, etc.? Just consecutive integers. Can somebody name a recurrence relation that describes this sequence?
A n minus 1 plus 1.
So the nth term is the n minus first term plus 1. And maybe an initial condition a1 is equal to 1. There you go, that describes that sequence. What about factorials? 1, 2, 6, 24, 120, 720. This is 1 factorial, 2 factorial, 3 factorial. Remember, n factorial is the product of the first n integers, starting with 1.
A n minus 1 to the third? No.
Something like that. So this is A1. So think about it.
Is it a sub n minus? Oh no.
Yeah, keep working it.
Because it's like a sub n minus 1 times n.
Nice. So A5, for example, is 120, and that's 24 times 5. A4 is 24, and that's 6 times 4. And 6 is 2 times 3. So yeah, if you take a n minus 1 and you multiply by n, you get a sub n. So yeah, this is a recursive function. Someone asked in chat. And again, an initial condition a1 is equal to 1. Alright, how about this sequence? Some of you have seen this before.
Fibonacci?
That's the Fibonacci sequence. So how do we find the nth term of the Fibonacci series or sequence?
It's the number before plus itself.
Almost.
1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5. That's the number before plus itself, is it not?
So the nth number is the n minus first number plus the n minus second number.
Oh, yeah. Yeah.
Right, so yeah, what you meant. Right, so an is an minus 1 plus an minus 2. And that helps us find a3, it's a2 plus a1, but it won't help us find a2 because that would be a1 plus a0, and we don't know what a0 is. So we have a pair of initial conditions. We describe exactly what a1 and a2 are equal, but then for n bigger than or equal to 3, the nth term is the n minus first term plus the n minus second term. That's the Fibonacci sequence. And we'll come back to that in a few weeks, and we'll actually derive this from looking at populations of rabbits. And we'll see some wonderful things about this. All right, so those are recurrence relations, and let me give you one more example. There was a time when you could put money in a bank and you could make money off of it. Doesn't really happen much anymore. But when I was a kid, if you put money in a bank, you got like 10% interest every year. So if you put $1 in, at the end of the year you'd get $1.10, and at the end of the next year you'd get 10% of that. And that was pretty exciting when you were a kid, right? But it's not exciting the first year because you got $1, you could go buy a candy bar, but instead you put it in the bank, and after a year all you've got is 10 cents. Right? It's not that big a return when you're a kid, but it's actually a great return. It's enough to live on if you can find it. So we can describe how your money would grow under this yearly interest as a sequence. So let's suppose we get 10% interest. This doesn't happen anymore. Some banks charge you for keeping money in them.
It's like 0.07 or something.
Yeah, I know. It's
really
like
dumb.
you need a better calculator just to like get that small. But let's suppose there's 10% interest, right? And so you start with some original principal. Let's say you put $1,000 in. And so after 1 year, you have your original amount plus 10% of that original amount. And after a second year, you have whatever you had at the beginning of the first year plus 10% of that amount, which is P1 plus, and let's simplify this. 1 times P0 plus 0.1 times P0 is 1.1 times P0. This will be 1.1 times P1. P3, if you do the same calculation, will be 1.1 times P2. And after 4 years, you've got 1.1 times what you had after 3 years, and so on. Well, you can go back and you can substitute, and you can say, well, P2 is 1.1 times P1, which is 1.1 times, well, what's P1? It's 1.1 times P0, which is 1.1 squared times P0. P3 will be 1.1 times P2, and if P2 is 1.1 squared times P0, this is 1.1 cubed times P0. P4 will be 1.1 to the 4th P0, and so on. And so you could find an explicit formula for how much money you have after n years, which is something like 1.1 to the n times your original investment, P0. But we could also define this as a recurrence relation, which is simply Pn is Pn minus 1 times 1.1, and P0 is, whatever your original investment was. So there's the recurrence formula. But here's kind of an explicit way to calculate Pn, and you can see where you're getting this exponent in how much money you make. And so after a couple of years, you're not making a whole lot, but after 50 years, this is a pretty significant multiplier. This also works when you're paying interest, like on a car loan or a home loan or a student loan. The longer you go, the bigger this exponent gets, the more you end up paying, until eventually you're paying 2 or 3 times the original principal.
People pay student loans for 20 years and have more left over than they did when they started.
Yeah, and it's even a scarier when you're doing something like real estate, and you buy a house and you're paying a mortgage on it, but you're paying a huge interest rate, and after 20 years you may end up owing more than the house is worth if the market has declined, and you may not be able to sell the house because you can't afford to sell it because you're not going to get back enough money to cover the payments you have left. All kinds of nefarious things.
2007 flashbacks.
Yeah, right? So don't get me started on money, though. We need the Star Trek model, you know, where there's like enough stuff for everybody.
For real.
Is that how, I don't know anything about Star Trek, is that their economy is, they just have enough resources where everyone is rich?
Apparently, and I don't know all of the backstories and stuff, but the comments they make in passing is, you know, there's no currency per se in the Federation. I mean, you have access to food and medical care and housing and education and things like that. But then there's like Ferengis with their gold pressed latinum and all that, so it's always there. All right. All right. So we'll come back to those multiple times, but that's the first pass of it. Let's look at another thing you've probably seen in some form, which is summations. So we're forgetting about sequences for now, right? We're just back to just plain old symbology. So suppose we want to add up a series of numbers. For example, x1 plus x2 plus x3 plus x4 plus x5, where these are, you know, defined somewhere. We have a shorthand for writing this expression, which is to write a summation symbol. This is an uppercase S, Greek letter. We can say sum I equals 1 to 5 of x subscript I. And this means exactly the same thing as that. It means write down x1, 2, 3, 4, 5, right? Take the subscript from 1 to 5. We're going by integers. And then add them all together. And this is like a for loop in C. We could have a sum that we initialize to 0, and then we could say for I equals 1 to 5, sum equals sum plus x bracket I. And that would add the ith element of this array to this running sum, and when we're done, our sum would be equal to whatever this is. And just like when we do this in a for loop, the symbol I is arbitrary. This is also equal to the sum from j equals 1 to 5 of x sub j. It's also the sum from w equals 1 to 5 of xw. And we can play around with subscripts. I could also write this as the sum from I equals 0 to 4 of x subscript I plus 1. And it's exactly the same thing.
Reviewing from calculus.
Say again?
I feel like I'm just reviewing calculus.
Awesome.
I did Calc 3 last term.
Yeah, this is the stuff that gets us into integrals, right? Riemann sums. We won't get quite that bad, though. We'll stick to integers, and we usually won't go too infinite. So I could do, you know, I is equal to 0. This means x1. I is equal to 1. It means x2. I is equal to 3 is x3. 4 would be, 3 would be x4. When I is equal to 4, the last value, this would be x5. So this is exactly the same as that. And more generally, you know, if we wanted to write x6 plus x7 plus x8, we could do the sum for I equals 6 to 8 of x subscript I. So it's purely a shorthand. And so I'll post new homework on Wednesday, and there'll be a bunch of exercises around some of these concepts that you can get your hands dirty with. But it's mostly just familiarizing yourself with definitions and doing the legwork. So we should note if we have some function f of I and we want to add, you know, c times f of 1 plus c times f of 2 plus c times f of n, right? This turns out to be the same thing as just doing the sum of f of I and then multiplying that sum by c. If we have a pair of functions f of I and g of I, and we wanted to take the sum of f of I plus g of I, that turns out to be the same as this. And so this is definitely calculus flashback time, right? These are properties that we have for Riemann sums. If you want to take the integral of, you know, some constant times a function, you can pull that constant outside the integral sign. This is why. If you want the integral of the sum of two functions, you can integrate them separately and add those together. This is why. So we'll use summations to good purpose throughout the course. It'll be a handy source of examples of problems that we want to solve or proofs that we want to do. But there's nothing too deep going on. It's really just kind of a notational convenience. But it relates to things like doing for loops in our programs. So we can do double summations, and it might look something like this. And let's say we want to do the sum from I equals 1 to 5 of the sum from j equals 1 to 3 of a subscript I comma j. And one way to approach this is to just break up the problem. Let's just think about this inner piece. Forget about that thing in the beginning. What is the sum from j equals 1 to 3 of a I comma j? Well, that would just be whatever I is. I don't know what I is, but it would be a I comma j is equal to 1 plus a I comma 2 plus a I comma 3. That's what that thing in brackets is. And I is just a variable. I don't have a value for it yet, so I'm just writing it down as I. But this expression says set j equal to 1 and see what this is. Well, that's going to be I, a sub I comma 1. And then set j equal to 2, this is going to be a I comma 2. And then set j equal to 3, this is going to be a I comma 3. And the summation says add them together. So this is this, which means our original expression is really just a shorter way of writing this. And this is just a single summation. It basically means set I equal to 1. So this is going to be a1 comma 1 plus a1 comma 2 plus a1 comma 3. And then set I equal to 2. And so on until you get to I is equal to 5. And then because we have this summation, add all of those together. That's what this original expression means. And this is like doing a running sum inside a pair of nested loops. For I equals 1 to 5, curly bracket. For j equals 1 to 3, curly bracket. Sum equals sum plus a bracket I comma j, or function call I comma j. All right, and then one more property to note is, for example, if I wanted to do a sum from 1 to 10, I could do a sum from 1 to 7, and then I could do a sum from 8 to 10, for example. In other words, I can split this range up wherever I like, and I can say, okay, well, let's add terms 1 through 7, let's add terms 8 through 10, and let's add those together. But sometimes this is useful. Sometimes we may be trying to find a sum and we have no idea what it is, but we can break it into 2 or more pieces and figure out what those individual sums are and then just add them together. Alright, and then the last thing worth mentioning is that these sums can be infinite. So you may see something like, the sum from I equals 1 to infinity of 1 over 2 to the I. But it's exactly the same meaning. This means set I equal to 1, this is 1 over 2 to the 1. Set I equal to 2, this is 1 over 2 squared. Set I equal to 3, this is 1 over 2 cubed. And so on, and then just add them all together. So this is an infinite series. And it means the expression you get when you add up this infinite number of terms. But as you probably know from calculus, sometimes even though we're adding an infinite number of things together, we don't end up with infinity. We get a nice finite number. In this case, this sum is always less than 2. It's always less than 1. But it gets really, really close to the number 1. It's a half plus a quarter plus an eighth and so on.
I don't think it's 1/3 count.
Yeah, this one comes out to 1. But sometimes this does not end up being any kind of real number at all. It just gets bigger and bigger and bigger as you keep adding these terms. It'll get larger and larger, and there's no number that it's getting closer and closer to. So that gets into like convergent, divergent series and all this stuff that we're not going to do, but that you've done or will do in calculus classes. Alright, so last thing to talk about for this unit is matrices. If you've done or are doing linear algebra, some of this may be familiar. Matrices are ways of representing multiple things in a succinct form. Linear algebra is 3 courses in one. It's a course on higher dimensional geometry, planes that sit inside 6-dimensional space, right? Things like that. It's a course on matrices, and it's a course on solving simultaneous equations. So linear algebra, or the subject of linear algebra, is 3 subjects in one. And sometimes it's taught from one perspective, sometimes from 2, sometimes from all 3. If you can learn it from all 3 perspectives, it's a really, really rich experience. But the reason matrices are so important is because in the discipline of linear algebra, matrices are one way to study simultaneous equations. And simultaneous equations pop up all over in the day-to-day world. For example, I'm doing flashbacks already, so let's do another one. KVL, KCL from Engineering Computer Science 120. Everybody remember that? So finding currents and voltages in circuits and the arrows with the circles going around and resistors and all of that stuff. We won't do that. But remember, the punchline at the end of doing a KVL, KCL analysis was a series of equations. And you had to solve those and find values of currents or voltages that made all of the equations true simultaneously. All right? And one way that you can do that, at least when I taught 120, I told students they could use MATLAB. And there's a way that you can write an equation of matrices that will give you the solutions to those equations. You can also do it by, modifying the equations, finding common variables, and subtracting and eliminating variables, and so on and so forth. That's all linear algebra stuff. If you are buying and selling stocks, right, and you have a risk associated with each stock, and what's the likely change in value of this stock versus its price, change in that stock versus its price. This stock is really, really cheap, but probably not going to perform very well. But it's really cheap. I can buy 1,000 shares for a few bucks, This stock is really expensive. And it's such a powerful company, so large, it's probably not going to gain a lot of value, but it could lose a lot of money. It's probably not worth me investing, right? So you have, 5,000 stocks you can choose from, and you want to know, well, what should I put in my portfolio? Given what happened yesterday, this company increased in value, this company's president started coughing during a press conference. How should I adjust my holdings in these stocks? Well, you can reduce that to a series of, 5,000 equations that you need to solve simultaneously. And so one way to solve simultaneous equations is by using matrices. And it's probably one of the main reasons that we study matrices in computer science. One of the reasons linear algebra is required to do junior level CS work. If you do computer graphics and you're trying to figure out, which objects are obscuring which objects in a three-dimensional field of view, or where are the shadows being cast from this light source with these objects, right? That's all matrix manipulation. Here's an object I want to turn in space. How do the coordinates change when this thing rotates, 30 degrees along this axis? That's all matrix manipulation. So let's just go over the basics of matrices. And this is not a matrix course. That's what linear algebra is for, Math 215. But let me just highlight a few of the higher level ideas here, and we'll use some of this later on when we talk about graph theory and such. So what's a matrix? It's a bunch of numbers written in a rectangle. That's my non-mathematical definition. So write down some numbers, 2, 3, 4, 1, negative, 1, 0, 2, 6, 11. Throw them in parentheses, there's a matrix. So a rectangular array of numbers with, certain number of rows, certain number of columns. And I'm going to pin down some notation. I can write these elements as subscripted variables. So Aij is the element in row I, column J. So rows go down like this and columns go across. When we do some graphics in 223, we'll revisit this. But I'm going to standardize rows are going down, and that's going to be the first subscript, and columns are going to go across. That's going to be the second subscript. And so we could write a matrix A as something like this, just a set of Aij. But however we decide to denote it, it's a bunch of numbers in some kind of rectangle. And so we can do arithmetic on matrices. And addition and subtraction, totally straightforward. So here's one matrix. 1, 2, 4, 6. Here's another matrix, 4, 8, negative 2, 11. And if I want to add these together, I just add element by element. 1 plus 4 is 5, 2 plus 8 is 10, 4 plus negative 2 is 2, 6 plus 11 is 17. There's my addition of matrices. And subtraction exactly the same way, just subtract element by element. So addition and subtraction, pretty straightforward. Multiplication is a different story. So multiplication, we do something very odd. So we're going to get a big matrix out of the end. But this term in the upper left corner, we're going to get by taking the first row and the first column and doing what's called a dot product. So a dot product says multiply the first element of each of these vectors, multiply the second element of each of these vectors, and then add those numbers together. So this is going to be 1 times 4 plus 2 times negative 2. Right? 1 times 4 is 4, 2 times negative 2 is negative 4. That's going to turn out to be a 0. Alright, the upper right corner, we're going to take the first row and the second column and multiply those. And we're going to get 1 times 8 plus 2 times 11, which is 22, and 8, that's going to turn out to be 30. The number down here, which is in the first column, second row, so we're going to take the second row and the first column, and we're going to do 4 times 4 plus 6 times negative 2, which is 16 minus 12 is 4. And then the bottom right, we're going to take the second row, second column. This is going to be 4 times 8 plus 6 times 11, which is 66, and 32, which is, I think, 98. And so this matrix times that matrix is the matrix 0, 30, 4, 98. And it might be a goofy thing to do, but that's how we do matrix multiplication. Alright, so one of the cool things about matrix multiplication is in general it's not commutative. AB is not the same as BA. In fact, some matrices you can't even multiply together. They have to have the right relative dimensions. And so I might be able to multiply A by B, but B times A might not be defined because they might not have the proper dimensions. But even if they are defined, even if I just took these and multiplied them in the opposite order, I would end up with a different matrix. So it's not commutative. Alright, the next thing is there's an identity matrix. For example, the 3 by 3 identity looks like this. It just has ones going down the diagonal. And it's called the identity because if I take any 3 by 3 matrix and I multiply by I just get back the original matrix. And if I take the identity and multiply by any matrix A, I'll get back the original matrix. So that one's commutative. And so this is kind of like the number 1. You multiply 1 by a number, you get back the original number. Well, you multiply this matrix by A, you always get back A. And so we can define powers or exponents of matrices. a to the 1 is just a squared is a times a cubed would be a times a multiplied by a, and so on. And a special by definition, a to the 0 is, well, it's not 1, it's the identity matrix. So the identity matrix works like a 1. We can do what's called transpose a matrix. So a with a little power t on the top, a little superscript, equals a with rows and columns swapped. So if I have this matrix and I take its transpose, I'm going to basically take the first row and turn that into the first column, second row into the second column, third row into the third column. So I'm just hurling definitions at you here, but we'll come back and use them later. So a symmetric matrix is one that's equal to its transpose. So if A is equal to A transpose, then A is called symmetric. And what would it mean to say that this is a symmetric matrix? Right, there's a matrix if I swap the rows and columns. The first row becomes the first column, the second row becomes the second column, and the third row becomes the third column, and I get back the original matrix. So that's a symmetric matrix. And symmetric matrices are useful. Alright, we cannot divide matrices. There's no division operation. We can't really define A divided by B. But sometimes we can do something almost as good. So if you just think of algebra, if you want x divided by y, x over y, that's the same thing as x multiplied by 1 over y. And even though we don't have a divide operator for matrices, we sometimes have the ability to find the reciprocal of a matrix, or what's called the inverse. So A inverse is a matrix such that if you take A and you multiply by A inverse, you get the identity. And that's not always possible. But if there is some matrix that when you multiply A by it, you end up with the identity, that matrix is called the inverse of A. So I'll complete our CSE215 flashback since we're already right at the brink of it anyway. When we had our simultaneous equations from KVL, KCL, we changed them into a matrix equation that looked like this, where A multiplied by X should be equal to B, and we wanted to find what the matrix X was, and that turned out to be a matrix of, voltages or currents. Well, if we can find the inverse of A, we could do A inverse times AX equals A inverse times B. And this is the symbol for the inverse of A. And A inverse times A is just the identity, and the identity times X is just X. And so if we could find the inverse of this matrix of coefficients, and we multiplied by this matrix of right-hand sides, we would magically end up with this matrix X that was the solution to our simultaneous equations. So finding inverses is a powerful thing to be able to do. And a lot of computing power goes into solving inverses of matrices. And a lot of theoretical development and a lot of unusual computer architectures are devoted to trying to very quickly find the inverses of matrices. Because if you can do that, you can solve matrix equations, which means you can solve simultaneous equations, which means you can balance portfolios or optimize systems or things like that. Do computer graphics, rotate objects in 3 space and find out what the new coordinates of the endpoints are, and so on and so forth. So this is big business, calculating inverses. We won't go through how to find inverses here, but there are systematic ways you can do it that you'll study to death in Math 215. And they basically come down to solving simultaneous equations, eliminating variables, or doing tricks with determinants. All right, and then just a couple of other versions of this to mention. So 0, 1 matrices are, guess what, matrices containing only zeros and ones. And we might use this to represent in a computer information about some collection of data or some physical system. And we can define ways to do things like multiplication on these using logical operations. So Boolean products and so on. But for example, I might have 3 computers, A, B, and C. And I have connections among different computers, and maybe I want to store information about which computers are directly connected to which other computers. And so if I had this matrix, right, it would mean that A and C were connected to each other, but A had no direct connection to B. B was directly connected to C and also had a connection to itself, whatever that means. And C is directly connected to both A and B, and also to itself. And so with a matrix, I could represent, the connectivity among a set of computers. And this is a 0, 1 matrix where I'm saying a 1 means there is a connection, a 0 doesn't. If my computers had multiple connections among them, I might use a regular matrix, right? So it might be something like this. Which says A and B have 2 links between them, A and C have 4 links between them. And so close to the end of this course, we're going to talk about graph theory. And graphs are ways of representing connections among things. Network links between computers, acquaintances between people, roadways between cities. And one way that we'll store information about graphs in a computer is by using matrices. So we'll come back and visit this at that point. All right, so questions about any of this?
Could you repeat the 0, 1 matrices again? How you got 0, 2, 4?
Oh, totally separate examples. So this is a 0, 1 matrix. This is not. This is just a plain old matrix. So this was just an example of Booleans, and I said maybe this shows whether two computers are connected. But maybe this shows, you know, how many lines there are connecting two computers.
Okay, gotcha.
Okay. All right. Well, we have 5 minutes left. And normally I wouldn't start a new chapter in the last 5 minutes, but I'm going to start a new chapter in the last 5 minutes because I want to give you a definition, and this is going to be the most important part of this chapter. And so I want to give you that definition now, let you think about it for a couple of days, and then we'll start with that on Wednesday. So this next chapter is on propositional logic, and I want to give you a definition for a proposition. So a proposition is a declarative statement that is true or false. And that's it. That's the whole definition. A proposition is a declarative statement that is true or false. But I want to leave that hanging out there for a couple of days because this is going to be a really, really important definition to come back to. And a lot of what we're going to do in this unit, this is chapter 3 in the text, by the way, a lot of what we're going to do in chapter 3 is going to involve writing propositions. And if we're supposed to be writing propositions and we write things that are not declarative statements that are true or false, we should recognize that and know that we've gone off track somewhere. So here's some examples of propositions. My name is Nick. That's a declarative statement that is true or false. In this case, it happens to be true. 1 + 1 = 2. That's a declarative statement that happens to be true. That's a proposition. This is also a proposition. 1 + 1 = 5. It's a declarative statement. It's stating something. And in this case, the thing it's stating happens to be false. Because 1 + 1 is not 5. But it's still a proposition. Here's something that's not a proposition. x². It's not making a declaration. It's an arithmetic equation. It's an expression. It's a symbol representing what you get when you multiply x by itself. That's not a declarative statement. That's not something that has a truth value. Here's a different proposition. That is a proposition. It's stating that this is equal to this. That's also a proposition. This proposition turns out to be false, always. This turns out to be true, always. But this is not a proposition at all. And I'm making this distinction up front in the last, over the 5 minutes of this class, because as I said, most of what we do in this unit is going to involve propositions. We're going to study propositions, look at their properties, make new propositions from old ones, and eventually develop proofs that begin with one set of propositions and let us prove another set of propositions. But everything we do in there, we've got to make sure that we're dealing with propositions. And if we write something like this, then we're no longer doing propositional logic. All right, so that's the definition we're going to start with on Wednesday. I'll restate this, and then we'll start developing what's called propositional calculus or propositional logic. It's a way of doing calculations where instead of working with integers or real numbers or fractions, we're working with these declarative statements and combining them and checking their equality to one another and so on and so forth. And it's probably the funnest part of the course once you get into it. So we'll start from there on Wednesday. Come by office hours in the morning if you have homework questions. I have hours from 8 till 10 tomorrow morning. Otherwise, have a good one, and I will see you on Wednesday.